Okay, so this video is going to help explain the key theory behind some of the techniques that you're using for the sodium borohydride experiment, because having an understanding of what you're doing in the experiments will make sure that you sort of are more successful with the experiment itself, especially if you encounter any problems, because if you know what you're doing, you'll know how to sort of fix and correct them. So the sort of theory I'm going to cover relating to the borohydride reduction will be to do with the structure of the experiment. So this experiment is a good example of the typical structure you will see for most sort of synthesis experiments, and then I'll also explain how the technique of thin layer chromatography works as well. Okay, so most synthetic chemistry experiments will have sort of these sort of steps in their structure. So the first step is where you actually perform the chemical transformation that you're trying to do. So you're synthesizing the desired molecule, be mixing, stirring it together. Sometimes you might have to heat the reaction, sometimes you might have to do it at a low temperature, but you're trying to turn the starter materials to the product. Now the next sort of stage is to actually monitor the reaction as it's undergoing, and to see if the reaction is complete before moving on to the next stages. Because what you want to try and do is actually assess the progress of the reaction. Is it actually working? Am I forming the product? If it is working, is the reaction complete? Or if it isn't working, what is happening instead? Am I forming byproducts instead, or is it just staying as starter material? Do I need to change the actual reaction conditions to make it work? So rather than just sort of stirring things for a fixed amount of time and then moving on to the purification stages, without really understanding what's happened in the reaction, it's quite important to monitor the reaction, and you're going to be using TLC as the sort of main technique to be able to do that in this reaction. Then the next stage after you're finished with the chemical transformation is then when you're trying to do the purification stages. So there's usually sort of an initial, what we call workup stage, where you're using things like washes and filtrations to sort of isolate your compound as sort of a crude compound, with most of the sort of leftover starter materials or the reagents you've been using in the chemical reaction. And then if your sample needs it, then you'll have a further purification stage that you'll need to do. And then that should leave you with a final pure product. So then you move on to the final stage, which is where you do your analysis. Okay, so there's lots of techniques that you're going to learn in the lab, and some techniques you're going to learn how to analyze in the theory part of the course. And what you're doing when you're applying this to a synthesis experiment is you're trying to see if you've made the right compound, you've made the compound you're trying to make, and also how pure it is as well. And also what the other impurities are, if any are present. So in this experiment, then it follows that structure quite nicely. Stage 1, you're doing the chemical transformation by stirring at room temperature. You're then sort of monitoring the reaction using thin layer chromatography. You've got this initial purification, which is called an acid quench. So you're adding the solution to acid that will precipitate out the product, which you can filter. But this compound needs a further purification to make it really pure. So you're doing a recrystallization, and then you do your analysis at the end. Okay, so this is how thin layer chromatography works. It's perhaps one of the main methods for analyzing a chemical reaction, and the reason why it's a good technique is it's good at sort of analyzing mixtures and working out how many different chemicals you've got in a mixture, and also what those chemicals are. So you can use it to monitor reactions. So what you have when you're using thin layer chromatography is you have a TLC plate. This is what we call the sort of solid phase or stationary phase. Okay, so it's just an aluminium plate that's coated in a white powder called silica, and silica has this structure here. It's a silicon oxygen polymer, but it contains these sort of polar alcohols as well. So the silica, because of its structure, is a polar compound. And what you do is you take your TLC plate and you apply chemicals onto the bottom of the TLC plate, either your reaction mixture, or you can take a known chemical like your starting material, dissolve it up in a solution, in a solvent, and then add it onto the spot it onto the TLC plate. And then after it's been added to the TLC plate, you place the TLC plate in a tank, so a beaker with a solvent. And what will happen is the solvent, which is called the mobile phase, will run up the TLC plate, and the compounds that you've spotted from the mixture will also start to run up the TLC plate as well. And because chemicals will have different chemical structures, what will happen is they'll interact with the solvent and they'll interact with the silica in different ways. Okay, and it's all down to their polarity. Where you've got a very polar compound, so one with sort of a very sort of electronegative bond, and also functional groups that can hydrogen bond, these will sort of interact very strongly with the solid phase, with the silica. So as the TLC solvent is running through, they won't travel up the plate very highly. Whereas if you've got compounds which have less of an affinity, less of an attraction to silica, they'll run higher up as well. And that's what causes the different chemicals to separate out. It's very much like if you have done the experiment with a piece of filter paper and put some ink onto the filter paper and then put it in water. You see the different chemicals, the different colours in the ink separating out because they've got different chemical structures. Well, that's exactly what's happening with a TLC as well. And then so what you do is you sort of run your TLC in the solvent and then let the solvent run up to the top of the plate, and then you analyse and you see how far the spots have travelled up the plate to see what's in your mixture. And so the way that this is used to monitor a reaction is on your TLC plate you have some of your starting material. So this is what you know is going to be the ketone for the borohydride reaction. You spot a small amount of your reaction mixture on the plate, and then just a little bit of both samples in the middle as well, which we call a mixed spot or a co-spot. And then you place that into the TLC tank, let it run up the plate, and then you analyse and view the TLC plate under UV. And what you'll see is the chemicals have run up the TLC plate, and you'll be able to see under UV spots which you can then sort of circle to see how far these chemicals have travelled. And what you should see is that when you're monitoring a reaction, is if you've got sort of starting material present in your reaction, then you should see a spot of the reaction mixture matching the level of the starting material. And that's how you know that what you've got in that mixture of that is starting material, because it's running at the same sort of retention factor as the starting material itself. But we can also see is if you find a new spot forming that isn't your starting material, is that a chemical reaction is taking place. And that tells you that the reaction is working, you're forming your product. And what you also need to think about is actually the structure of what you're trying to do in your chemical reaction. So here you're trying to form an alcohol in the borohydride reduction, so you should be thinking about how that is a more polar compound than the ketone, so you would expect the spot to come lower on the plate than the starting material. And if you see that, that's great, that's confirming that it's the product that's forming. If you saw the spot that was less polar than the starting material forming, that would be a sign that there's actually you're forming something else in the reaction. But what this reaction mixture TLC shows is that the reaction is incomplete. So while you are forming product, you have starting material left over. So the way to analyse this TLC then is to go, right, okay, I can leave the reaction to stir for longer, I can heat the reaction up, or I can add more reagent. I can add more sodium borohydride in this example. And what you're trying to do here then is to get more of the starting material in your reaction to form the product. These are all three options that will help you do that. And then you analyse the TLC again, and we can see from the TLC of the reaction mixture on the right here, one spot, and that spot doesn't match the starting material. So we've only got product forming. So that is a sign that the reaction is complete, and then you can move on to the purification stages to work up and isolate your sample. And obviously you'd have a higher yield if you purify the reaction when you've only got a complete reaction with product than an incomplete reaction with starter material. So that's a good reason to monitor the reactions and make sure they're complete before moving on to the purification stages. Okay, so that's the summary of the key theory behind how thin layer chromatography and the general structure of synthetic experiments sort of work.